Welcome, everybody. This is JILA, so that you know when it says 12 o'clock, it's time to start the colloquium. We will also end on time. Those of you who are coming in late, learn from your mistakes. Meanwhile, welcome to everybody, researchers, students, staff, everybody. JR tells me that if we need help communicating with you, the staff can help us do that. So the aim of these talks is to try and connect the entire of the JILA community with what each of the groups is doing. I hope this is working on Zoom. It is. It is. Oh, okay. So the aim is to make yourself comprehensible, Graeme. What? What? And I know you're used to talking to experts, but treat us as though we're smart, but not necessarily expert. I understand there's going to be something to eat afterwards. Is anybody, Kim, what do you want to say what's going to happen afterwards?
Around 12:40, I'll set out some cold brew coffee,
And where will that be?
right there.
Just outside, there will be cookies and coffee and maybe something else after the colloquium, so you can gather and talk to each other about whether you understood what was going on. Graeme Smith is our speaker today, a JILA fellow. He joined JILA and CU Physics in 2016. He got his PhD in 2006, and he has traveled various places over the world. He's spent time in Bristol and IBM Research. If you're on Zoom and you have a question, please put it in the chat. Tyler McMacken is going to be monitoring the chat. And meanwhile, Graeme, I understand that you encourage questions from the audience.
Yes.
While you're talking. So you have 40 minutes, and then we'll end on the hour, so maybe 20 minutes of questions.
Sounds good. Thank you.
Let's give him a hand of...
Thank you very much. I really like this program, and I appreciate the chance to speak. Thank you for coming. So what I want to do today is give you sort of a flavor for a strand of research that we do in my group and people do elsewhere, studying the theory of quantum information. The base.
If you wish to remove your mask so that people can see your lips, if you prefer not to, you can keep it on, whatever you prefer.
I just leave it on, and then if you're having trouble, you can tell me. I'll take the mask off. I got all the shots, and okay. Anyway, it didn't switch. Okay, so the basic idea of quantum information is to try to marry these two sort of essential ideas from the 20th century. The idea of really information technology, and understand it in light of quantum mechanics. You might be interested sort of solely in finding sort of better ways to calculate stuff or better ways to communicate. But you can also, and I think this is really a more important way of using quantum information, use the perspective of information theory to find better ways to think about quantum mechanics itself. So information theory, it's sort of it's an old kind of engineering-y and mathy area that basically studies trying to communicate messages from one place to another, possibly in the presence of noise. So you can imagine your cell phone talking to your cell tower, and the messages either get corrupted or bounce off of stuff, and it's a total mess trying to get the message from your cell phone to the tower. And information theory kind of is a box of tools that allows you to send crisp digital information across noisy communication links. It started with this guy, Claude Shannon, in the 40s, and sort of by the end of the 20th century, all of the mathematical proofs that Shannon had in his paper were just sort of standard technologies that people use in their phones, in their computers, modems, that sort of thing. Quantum information theory grows out of the goal of having a sort of more accurate way of talking about information that includes the fact that the world is described by quantum mechanics. And the sort of philosophy of quantum information theory is somewhat different from the approach of, I guess, more traditional areas of physics. One of our goals is really to abstract away as much detail as we can to kind of find out, well, what are the fundamental limits that nature puts on information processing? We want to know, okay, you got a communication link, what's the best you can do with it? Goal 2 here, I think is even more important. The details that we're forced to leave in our models of communication systems reveal to us kind of what are the essential features of quantum mechanics itself. And this can help us understand traditional physics on condensed matter, high energy AMO. And furthermore, in a very practical way, well, strategies approaching the fundamental limits we find may be realizable. And sort of rule of thumb is if you find some fundamental limits, 20 years later, probably you can achieve it. And that's either today or in the future. So it's an area of work that's kind of about physics, but it's about a bunch of other things too, like geometry, computer science, engineering. It has a mathier flavor than many areas of physics. Partially, it's inherited that from computer science and information theory, so like we have notions of rigorous proofs and epsilons and deltas and stuff, and that can be off-putting a lot. But it also, I think, the most interesting, well, to me, the stories that we can tell about quantum information are the most important. And I sort of think of it as a collection of toy models of stuff that maybe in the real world you could actually realize, but sort of examples and simple models of effects that we might want to try to use or observe in nature. And one of the key differences between classical information theory and quantum is we have way more resources and much more interesting interactions between different sorts of resources. So what is the point of this sort of field of study? Well, we want to understand things like what are the resources, the communication resources available to us? How can we convert one sort of resource to another, and how do the different resources interact, and kind of what's the recipe for using the different resources together? I have a recipe for bread here, but if you don't know how to cook bread, actually you're not going to do too well with that recipe. Bread is really all about not necessarily the ingredients, but what you do with them in the process that you use to mix them. People joke that there are 2 other ingredients, which are time and temperature, right? Because anyway, does anyone know what this picture is here down at the bottom? This is the teleportation circuit. It's a nice example of how we can use entanglement, so quantum correlations between 2 systems, to do something together with some classical communication. Oops, that's very tiny. That you can't do without the quantum entanglement. And one thing I want to do, if nothing else, is give you a feel for entanglement and what it is, and kind of what makes it different from classical correlations. So here's an example. I'm sorry, I'm overwhelmed by all the screens. There's one here and here and here, and they're all the same, but a little different. Okay. Yeah, okay, good. There's a whole area, a whole field of comedy that involves quantum information jokes. And I'm going to leave them mostly out, but yeah, entanglement is one of the key features. So the idea of teleportation is the observation, I guess, is if I have a quantum system sitting over here, and I would like it to get over there, one thing I could do is I could measure it and tell the outcome of the measurement to my friend sitting over here, and then they could prepare some state. But because of the way quantum mechanics works, and specifically the uncertainty principle, if I measure one thing and then send the information over here, this sort of precludes the possibility of measuring some other thing and sending the information about what would have happened if I measured that. So I can only really get an approximate copy over on one side by just sending classical information. There's just sort of more to the quantum state here than the outcomes of a single measurement there. But teleportation, it kind of lets us get around this idea. We can use a pair of particles that are correlated. They got correlated because they were together at some point before. And if I have a state that I want to send, now I can use up this resource, this entangled pair, and I can do a measurement jointly on the state I want to send and my half of this entangled pair. And if I send the classical outcomes of that measurement, the receiver can apply a correcting treatment that actually gives me the exact state back out again. So by sharing this correlation between two parties, I now, together with sending classical information, or by sending only classical information, somehow can make a quantum state move from over here to over there. And this is, I guess, our first example of some non-trivial interaction between resources, because the entangled state alone is no good for that. It can't communicate anything from here to there. And the classical communication from here to there also is no good for sending the state, because in order to get classical information and send it, you have to measure the state. And once you measure the state, you can't measure it in some other way that would tell you some complementary information about it. Okay, so a key feature of quantum systems that makes this entanglement kind of not visible to us in everyday lives is that they're very, very delicate. So in a classical computer, you really don't care if the logical state of your computer sort of leaks out into the environment, or some degrees of freedom inside it. With a quantum computer, to respect the monogamy of entanglement, which we'll talk about in a minute, that's also a source of many jokes about quantum information, you have to make sure that not only does no information come from outside the computer and mess up your states, no information leaks out of the computer. Because it's going to turn out that if you leak information out of your computer, that's going to damage your entanglement and make your computer start to look more classical and less quantum. So one of the key challenges in building actual quantum computers and quantum communication systems is doing forms of error correction that let us store and manipulate quantum information while preventing any leakage out of the quantum computer. So I've got an outline here. We're going to talk about sort of the basics of quantum theory, and then I'll talk a lot about the monogamy of entanglement, because this is really, I think if I had to tell you one thing about entanglement, it would be that it's monogamous, and we'll see what that means in a moment. So a pure quantum state, it's just a little arrow, okay? So I can describe the state of my system with a little arrow. And if it's a two-level system, we call it a qubit, and it's just a little complex two-dimensional vector that points in some direction. And kind of all, you could imagine, I don't know, Euclid or something having an idea about these little arrows that point in various directions. But the thing that makes it different from just a study of little arrows is the fact that if you measure the state of your system, what happens is you have to tell it kind of a pair of perpendicular directions. And you say, I'm going to measure in this. And that measurement is going to give you an outcome that's either this way or that way. And the probability that you get this way is related to how much this vector overlaps with one. And the probability that you get this way is going to be related to how much this vector overlaps with 0. And the kind of complementary thing that I was telling you about before is that you don't have to pick a particular basis. Instead of these two vectors, I could choose to measure along these two vectors, and then I might get some different measurement outcome. But if I chose to measure along this pair of vectors, I can't later go back and say, wait, I changed my mind, I'm going to measure along this pair of vectors. When I measure here, if I get an outcome 0, I collapse down to this changed vector. I've disturbed the quantum state by doing the measurement. Now, what's she doing here? Did anyone ever think that a baby might be asleep? But you just wanted to check. And then you go check, and that's what she's up. But you did make some noise on the way in. So maybe if you had just left it alone, she would have been asleep. And I think these quantum states are a lot like babies, in the sense that there's sort of, well, I guess if I'm quiet enough, I believe I could check on a sleeping baby without waking it. But I've never gotten that quiet. And I can just imagine being in a lab having to do these experiments and these little babies that I accidentally wake up when I do the measurement. Just it seems like a very hard job, and I really like to be a theorist. I think this is as close as I want to be to doing these inevitably disturbing measurements. Okay. The communication links that we want to study and understand are, well, they're noisy. So oops, I skipped a slide. I'm just going to skip that slide. The theory of the world, quantum mechanics tells us, well, the states of your system are these little vectors, and all the dynamics are is that, well, the vectors get moved around, they get rotated around and around like this, and everything else is details. And these are important details, but if you just want to know how quantum mechanics works, it's just these little arrows that go around, and then you can rotate them all you like. And if you rotate these two, they stay orthogonal. And it's a pretty simple theory. It gets harder when you try to use it. You know, it gets simple when you only want to understand very simple things and basic things about the theory. It gets much harder when you want to start understanding like an actual system that you might actually have. But if you want to understand the structure of the theory, you can kind of abstract away a lot of the details and still leave some pretty interesting looking stuff. Okay, so what happens is the dynamics in our theory are just these rotations. Yeah, I have a vector, it just goes like this, donk, donk. But there is, oh, hi. There is a possibility that instead of there's this vector and then there's that vector, I might just not know which vector it's in. And to summarize my ignorance of which state it's in, I can sort of build up a matrix instead of a vector. And it's called the density matrix, and I just add up all the little vectors with the probabilities of being in those states. And the thing that I really love about this is you can think about the density matrix as having some uncertainty about what state you're in, or you can think about a density matrix as just being, well, there's some bigger system that I'm entangled with, and all of my uncertainty about the state of my system really is a reflection of how entangled I am with some other inaccessible system that I don't have control over. This is kind of why, again, we don't see very much entanglement. There's so much entanglement in this room, right? We're all super entangled with the environment. The trouble is we keep interacting with the environment and maintaining some entanglement with the environment. It's really hard for us to entangle with each other because we have to have some correlations with each other that are totally independent of all the other degrees of freedom. And there's so many things bumping off of us. They learn little bits about what our state is and cause the entanglement to kind of degrade in a way to make it look like this is a classical world. Okay, so that's what our noise processes do. Basically, I have a state, I'm trying to send it over here, and stuff bumps it and interacts with it. And I don't have access to all of the degrees of freedom that are interacting with it, so it looks like I've had noise added to my state. So at the output, I get some degraded version of the thing I put in. And oh, here's an example. Let's say I have a piece of optical fiber and I want to send some quantum state from here to there. I might encode it into some photons and then into the fiber it goes, but there are some degrees of freedom that absorb some of the light. Yeah, and I don't have instant access at the output to those degrees of freedom. And the fact that that information about the input got absorbed by the light introduces a sort of noisy evolution into the state that I've tried to send. So next, I would like to tell you about monogamy of entanglement. And I assure you you don't have to worry. It looks bad with this outline, but it will be fine. We will end on time as per Professor Hamilton's demand. Okay, no, it's a good rule. So the key feature that I've been talking about of sort of noisy processes is that if I have a quantum state and I let it interact with some other degree of freedom, it's going to get entangled with that degree of freedom. So here's a picture of kind of like the simplest or the most famous way of making two little two-level systems interact. It's called a controlled knot. And all it does is it says, hey, if this top wire, this first qubit, is in the 1 state, so that's a particular direction on that circle, then flip the state of that one. So it's like if the top state is pointing up and the second qubit is looking like this, then flip it back and point it the opposite direction. But if it's pointing down and the second qubit is pointing like that, then just leave it alone. So it's just like literally switch the direction of this arrow if this arrow is pointing up, and leave it alone if it's pointing down. And you can use this actually together with just single qubit rotations to do any rotation you like. And that's why it's sort of okay enough for us to say, hey, we're just going to think of the world as a bunch of little C knots interacting, making our qubits interact. And we're going to try to understand sort of, well, first of all, how entanglement arises, and second, why it's so hard to see. You can prepare a highly entangled state actually with just this C knot by taking a superposition of sort of an up and a down, and applying to that superposition the C naught. So now you end up with a sort of entangled state. This is the canonically maximally entangled 2-qubit state, which has the property that whatever measurement I do over on this side, I end up with the same outcome in the measurement that I do on the other side. So that's the sort of strong connection that the 2 qubits have when they're entangled. Of course, lots of things are correlated in the world, right? Like not all correlation needs to be entanglement. Whenever my clock says, well, if my clock says 7, chances are I'm awake. I'm not entangled with my clock. It's just a classical correlation. The thing that is different about entanglement is monogamy. And the thing about monogamy is basically, here's what it is. If 2 systems, A and B, are maximally entangled, so that means they have sort of the most quantum correlation they could have. All of the variation in this state is explained by entanglement with that system. Then the 2 systems have perfect privacy. Nobody else in the world knows what the measurement outcomes of this state are. And the same for that. So the only thing that can happen is if I measure, then I can perfectly predict what you're going to measure if you measure in the right way. But the fact that we're maximally entangled means nobody else can have any predictions whatsoever about what we're going to, what outcomes we're going to get when we do a measurement. And actually, the way that classical correlation, you can see how this is going to be a problem. If a system starts off maximally entangled with another one, these 2 are maximally entangled, my fists, but this one keeps interacting with other systems. At some point, they may learn a little bit about what's going on in this system. And if they learn a little bit about what's going on in this system, they degrade the entanglement between these 2 systems. So I can prepare a quantum state that's entangled by having a single interaction between these 2 systems. But if a third party comes along and interacts, tries to do exactly the same thing we did to get entangled between these 2 systems, but I don't, but sort of goes away, that interaction actually causes the entanglement to go away. Now it's just a classically correlated randomness, a boring pair of coins that always say the same thing, but there's nothing, you can't use it to teleport. There's nothing quantum about it. You can't violate Bell inequalities. You've just destroyed the entanglement by actually trying to make this thing also entangled with that thing. And in fact, that's kind of why the world looks classical. The degrees of freedom constantly interrogating the state of our systems make it impossible for us to have entanglement between, say, elements of this computer. And basically, we can think of a classical, and the way I like to think of a classical computer is that it's a quantum computer, except there are just an eavesdropper. There's an eavesdropper on each wire in the quantum computer, just copying down everything that the computer says. And that is all it takes to make the quantum computer stop being quantum, stop having superpositions, stop being as powerful, and start just looking like a classical machine. And basically, the eavesdroppers in this case are sort of all the little degrees of freedom in my computer that we don't have control over, but that nevertheless learn information about the logical state of the computer. You can imagine why it's hard to make entanglement now, right? Because, well, you have to control everything. You have to fully control who learns about the state of your system. And doing that is super hard. You have to kind of isolate things, but then you have to go in and be able to poke them as well. So I've kind of argued that entanglement can happen or arises due to any interaction. But there are too many interactions. And those interactions kind of try, like this case, like down here, this interaction is trying to make entanglement between this wire and that wire. This interaction did make entanglement between that wire and that wire. The problem is, if these two are already entangled and I try to make more entanglement with this and that, I'm going to end up breaking the entanglement here and sort of basically learning some information about the state, but not all the information about the state, and therefore make the state look kind of more classical. And that's why, even though entanglement is all over the place, even though I'm entangled with all of the environment in this room, and all of us are entangled with the rest of the universe, that's what gives us our entropy. Nobody noticed it really. The reason is, well, it wasn't discovered before the 20th century. It wasn't discovered until the mid-20th century, 50 years after people come up with well, it wasn't understood correctly even later, but 50 years after quantum mechanics, people still didn't really understand entanglement, and that's because of its monogamy. If you want to have entanglement between two systems, you have to ensure that neither one of them leaks any information about its state to any other systems. And most systems in nature, they interact very strongly with their environment, and because of that, they become entangled with the environment almost immediately. And that destroys any previous entanglement that they had that used to be there between the internal degrees of freedom. So this is kind of I guess, the modern way of thinking about how classicality arises, which is that, hey, it's not that big things necessarily get classical, it's that bigger things tend to interact more with their environment. And if you get a thing that sort of interacts a lot with its environment, it gets really hard to see that thing behave in a kind of quantum way because superpositions get, quote, collapsed by this interaction with the environment, or any entanglement gets decohered by interactions with the environment. And the idea of really Zurek and Blum-Kohut and friends of quantum Darwinism, they call it, is that basically things start to get classical because of all of these sort of consistent, enormous number of interactions between systems that you're trying to enhance and make quantum, but which keep leaking information to the environment. So that's kind of why, I guess, even though there's all this entanglement all over the place, entanglement is also responsible for creating a world that looks classical. So let's look at information theory. We want to take this feeling or this idea of entanglement and its monogamy, and the fact that entanglement gives rise to noise because if we become entangled with systems that we don't have control over, and understand how we can use quantum correlations, or use entanglement, but also use noisy communication links to send noiselessly to protect the entanglement that we're trying to establish. So a key notion that we have to understand here is the capacity, communication capacity of a communication link, and it's just how much stuff you can send from one place to another. So here I have a truck. I don't know how many tons it could be. It could haul per load, but I bet I could ask someone in Comps 2 and they'd figure it out. And you know, a classical channel, I could also ask you about what's the most information you can send across it in terms of bits per channel use. So the channel capacity is literally just defined as use the best encoding you can think of and encode in your message into a bunch of uses of your communication link and do it in a way that at the output you can figure out what the message was. And if you can do it if you can do a good job getting the message out here, you call that a good code. And the number of bits you can send per channel use with the best code you can come up with, that's just called the capacity of the channel. That's, you know, how much information you can squeeze through the channel. And, you know, here's a picture of a bunch of channels. Does anyone know what this is? This? It's a compact disc. And these are pits on the compact disc. This is actually a very interesting channel. It's only possible because of sophisticated error correction strategies. These pits on the disk, you know, people would be very mean to these things and like slide them around and they get scratched, and they still work. And that's because of really powerful error correcting codes that are used in the encoding of these pits that let them tolerate, well, the noise process in that case is like what happens if someone, you know, puts it down on some sand and does that. This is a router, a fancy one. This is a optical fiber, and again, your phone talks to cell tower. At the level of information theory, we care only a little bit about how these things look, and we really only care about what's the output given the input. We just care about this probability, this conditional probability distribution. If I put in signal X, what's the chances I get out signal Y? And from that, we can figure out sort of a mathy formula for the best rate you can get when you communicate over a noisy channel. And then you can go back and you can try to figure out what P of Y given X is for optical fiber, for this, for that, for that. And then you can feed it into this formula called the capacity formula. And it'll tell you what's the most number of bits you can send. And it even comes with kind of a recipe for generating error correcting codes that can achieve that capacity, but only kind of, because the recipe is really a funny one. Does anybody know what you should do? Like if I said, okay, I have a channel, what kind of encoding strategy would you use? Mostly likely you say, I don't know. Okay, so the funniest thing in 1948, I would say, was probably this. The answer is, you don't know what code to use. That's fine. Choose one at random. What message should I use? I don't know. Choose a bunch of random bits. Choose another. Choose another. Okay, choose enough. How many is enough? Make sure you don't choose more than is allowed by this capacity. Choose up as close as you like to it. Choose them randomly. They work. There's just high probability they work. There's a whole like moving from that to actually building up a set of codes that are good for a particular channel is a big job. It's sort of like the second half of the 20th century. But to me, it's just kind of hilarious that this is like one of the most powerful ideas, I think, in math. You don't know what the thing is you're trying to make. Choose something at random, see if it's good enough. And in this case, it is. So one of the key features of classical channel capacity is that this formula, this clean formula, depends only on a single use of the channel. So I get to maximize this measure of correlations. It's called the mutual information between the input and the output. And I get to do it on a single use of the channel. And that's because of really nice feature of classical information theory, which is that if I want to know how good is this blue wire to me and how good is, does anybody know what this is? Do you? I remember thinking it was the stupidest thing in the world that they were going to do all this Wi-Fi. It's so buggy and hard to use. Why didn't they just put wires in every office? But I guess I was wrong. Okay, anyway, these two wires, using them together, you don't get any benefit. The capacity of the blue wires together with the gray wire is just the sum of the capacities. And the codes you use here don't have anything to do with this thing. And that's generally the story with with classical information theory. The story is, yeah, things are pretty additive. They interact trivially. If you make a smoothie and you add more pineapple, it tastes more pineapple-y. Over here, quantum is more like baking bread, you know, quantum information theory. There are all sorts of different interactions that are hard to control and hard to understand. And you might really, you know, have something great come out if you use the different resources together in the right way, or you might really have something terrible happen if you don't quite use them right. So I guess if I had two messages from this talk, the first is the monogamy of entanglement is the key feature of entanglement, and it's also the key reason we don't see entanglement much, because it's hard to make things. It's hard to make two physical systems monogamous. And the second thing I would say is that if classical information theory is like smoothies, quantum information theory is like baking bread, and it's really much more about taking different and incomparable sometimes resources and putting them together in ways that are advantageous to you. So in my last 4 minutes, I will talk a little bit about capacities in the quantum setting. So this is not an especially new idea. The earliest the earliest hint of this is this paper by Jim Gordon in 1965, where he looks at how optical communication, and he introduces all sorts of things that, you know, people didn't really come back to. Well, Holovo in the Soviet Union found sort of an analog of what Gordon was talking about here. But it was probably the 80s before people really started to talk about the sorts of things that were already in this paper. It's a really cute paper. I would look at it if I were you. It's fun. So these sort of older ideas, though, were about how quantum noise is this enemy that's going to make it harder for us to communicate. But a more modern view arose in the 70s and 80s that actually quantum effects could do something useful to us, for us. We could maybe enhance privacy in our communication, and maybe even we could do quantum error correction, and we could build systems that have large-scale entanglement and use those to do computation, communication, cryptography, and so on. So the quantum channel capacity is really just like the classical capacity. It's how many qubits you can send from one place to another. And actually, there are many capacities for a quantum channel. There's the capacity for sending qubits, for sending private bits, that's related to cryptography, and for sending classical bits. And each one of them, there's just some different capacity. I'm choosing to focus a little bit more on the quantum capacity, which is just, well, it's the same picture. You take a quantum state, you know, a little vector in a very high dimensional vector space now, and you encode it into the inputs of some noisy channel. Yeah, and then you want to make sure that at the decoder, the outputs of the channel, even though they jostle everything around and they bump into everything and they start to decohere stuff, the degrees of freedom that you spread across these channels can be recovered by doing a decoding operation. And then the capacity, it's just the best thing you can do, the maximum number of qubits you can send per channel use. And I will, at this point, say there is some math. And it tells you how well you do if you do the same thing that Shannon did. Just choose a random encoding. I mean, what else are you going to do? And that math tells you, and it's not, you know, it took people a while, but they figured it out, that this thing called the coherent information is the best rate you can get by choosing these random codes. And in the last 1 minute, I will tell you the fact that quantum capacities act like bread and not smoothies means that this random coding strategy is absolutely not the best thing you can do. And we don't understand the best thing you can do. We know a bunch of examples where you can do better than the random coding. And one of my favorite little problems to work on is finding better ways to think about generating error correcting codes that exceed this coherent information by introducing, well, entanglement between different uses of the channel in a sort of a systematic way. And what's missing seems to be, I think, that we don't quite know how to think about quantum information correctly, yet we're thinking of it in a very classical way. And that's why the analog of the classical capacity approach doesn't work as well as it ought to. And my hope is that we can figure out better ways by developing simple examples of noisy channels that for which these random codes don't work very well, and find out better ways, do some other math and have some other formula that tells us a better formula for designing the error correcting codes that we need for a particular channel use or a particular noise model, and then use the ideas from that to develop better methods of quantum error correction. So in summary, no, I gave a summary. Okay, look, in summary, monogamy tells us that if A is maximally entangled with B, nobody else in the world knows anything about A. Yeah, decoherence and classicality, they come from the fact that the world is constantly trying to copy your information. And once they copy it, even imperfectly, they degrade the entanglement between A and B. And the other thing I guess I wanted to emphasize was the interaction between noisy quantum resources is not additive, it's more like bread. And this is a challenge because it makes it really hard to understand the sort of very simplest quantities in the theory, but it's also an opportunity, as all challenges are, because it gives us the possibility of finding better recipes and better ways of fighting quantum noise. And fundamentally, it's all about trying to find the right way to think about quantum error correction and quantum information and how to encode it in a way that is robust to these things that keep bumping it and trying to learn about it. I didn't talk about this last part because I miscalculated. I want to show you my students and my group. This is a recent group meeting photo, and I hope that no group meeting photo will ever look like this again, because it was really not very pleasant to spend a year talking to people only through Zoom. Thank you. Yeah. Oh, that's yours.
Thanks very much, Graeme. I think that was a very effective use of this JILA auditorium channel to communicate between you and the rest of us. I'm going to let you pick out the questions, invite people to raise their hands, or if you're on Zoom, hit the chat. And so you can take care of that.
Okay, okay. So if nobody puts their hand up, I'm going to start picking. Yeah.
I'm worried about this monogamy of entanglement. Does that mean I have to get married, or can I choose to remain single?
You can choose to remain single, and you can choose to be entangled with one other partner. What it means is that if a third person or a third party comes to be involved, they can become entangled with your relationship with your partner, but they cannot become entangled with both you and your partner. Does that make sense? The third party, or the third system, always becomes basically, if two systems are maximally entangled and a third system comes and interacts with them, the best that usually happens if they make a good attempt at sort of becoming entangled with one of the systems is that they become entangled with the relationship between the two parties rather than either one of the two parties. David.
I remembered, many years ago, Dave Wineland gave this great talk called "The Quantum Watched Pot Never Boils," right? And
Yeah.
this was sort of this idea that, if you had an atom, in his case, in some excited quantum state, and you kept measuring it, right?
Yeah.
And you'd project it back, with some high probability back into the excited state, and he would prevent an atom from emitting light by measuring it. Now, I'm just sort of wondering, is there any connection between that and your idea of that, we're trying to, we're like a third party trying to entangle with our atoms and thereby turning it into a more classical object? I don't know if I can phrase the question, but you understand what I'm saying? This idea of that the measurements that Winan was talking about,
Yes.
is a type of third person breaking into the monogamy of maybe the entanglement of an atom between its ground and excited state.
So let me see. The effect, okay, the way I understand that effect, the quantum Zeno effect, it's called,
Right.
is more in terms of, I guess, the sort of information disturbance trade-off. As I extract information from the state, I disturb the state. And that particular proposal is designed to disturb the state back up to where it was, right? And I don't know a good way to describe that in a purely unitary way, which is what I would like, what you would like to have, right? You would like to be able to say, it's not really measurement, it's really entanglement between my measurement device's environment and the system is kind of pushing the system back to where it was. So I don't know the answer to that, but I believe it can be done. But that's only because I'm a zealot that believes measurements are pretend.
How do I think about monogamy in the context of GHZ states?
Yeah. It's a good way to think of it. Here. Is there a whiteboard? Should I use the whiteboard instead? Okay. Here's the way to think about it, I think. Okay, so okay. Yeah.
If you're on Zoom and wondering why everybody's laughing,
Oh, good.
None of the chalk works.
Okay, so first here's a maximally entangled state on two systems. Yeah, and monogamy of entanglement, I can state it, I guess, more precisely, which is that if I have system A and if system A is in some pure state with system B, then system C comes along, system C knows nothing about system A. Okay, so that's kind of the statement of monogamy of entanglement. Now, what happens with a GHZ state? It's actually quite interesting. Here's what happens. So I start with this, yeah, so I can make it like this. Okay, now I've made this state. So now someone will come along and try to make a copy here. Now we've prepared a GHZ state. So what monogamy of entanglement will tell me is if A is in some pure state with some other system, then it can't be correlated with any other system. Here, it's only in a pure state with B and C held together, right? So it's sort of, it satisfies monogamy in that sense. But the other thing that's happened now is by trying to make a copy of the B system, system C, if I just look at what's going on in system A and B, then I end up with a totally classical correlated state. I have a 0, 0 now plus a 1, 1. So we can say that the giant system is in a pure state, and therefore A is purified by both B and C. However, if I just look at the AB system, they're now in a classical state. And this connects to this quantum Darwinism thing, where we imagine actually that there are like a million of these systems that have made a copy. So now A has some entropy, and it's purified by a million systems. So it's maximally entangled with that. But from a very practical point of view, you don't have control over most of them, so it always just looks classical. Does that help? Does that answer your question? Okay. Is there anything on Zoom? Maybe people. Oh, hi.
So I guess most of the algorithms we're talking about recently are based on qubits and two-level systems.
Yeah.
So I was wondering if there are any fundamental advantages of by considering like three-level system and qubits or things like that.
Yeah. Okay. So, I mean, the answer is yes and no, because in principle, right, you can always, just like you can always write a number in binary or in hexadecimal or whatever, you can work in whatever base you like, and there's really no sort of difference in difficulty of doing multiplication in hexadecimal or binary or something like that. But the answer is yes, in the sense that the overhead of making that translation can be significant. So significant in the sense that specifically if you are trying, let's say you naturally have a three-level system and you're trying to do Shor's algorithm and you want to do multiplication using the three-level system. It's probably best not to first make everything into qubits and then use the qubit algorithm and then go back again, because it's going to have some like inefficiencies in the way in the way the translation works. So at some level, it's always best to look at the machine you've got and use everything in the most direct way, because also right now we don't have good error correction at the moment. So you just want to I guess you don't want to accidentally have to do extra gates, even if it's just a few. But at some fundamental level, the overhead is not too much to map from sort of one base to the other. Does that make sense? We can.
We just forgot about the concept of this.
Yeah.
Algorithm can speed up the process. Three-level system, three states is better.
Maybe you can repeat the question.
Oh yes, the question is there some dedicated algorithm that you use as three-level systems that is kind of better than the analogous algorithm using two-level systems? I know of some examples, like the Microsoft crowd, were designing directly for their topological qubit project, and I believe they have some paper about doing, I think, multiplication on three-level systems where they got a lot of simplifications. The thing is, let's say you had some great algorithm that works really well on three-level systems. Then what I will do is I will say, well, instead of each trit, I'm going to use 2 qubits and I'll encode it. And there's going to be a slight overhead in doing that, but it's not a huge one. So kind of there will be advantages, but not big enough advantages to go off and start re-engineering everything. I saw hands up here.
So how does the robustness of this monogamy kind of scale with the number of systems that are entangled? So like in this previous example, you have system A and B, and C comes in and it observes B, and then the entanglement's completely destroyed between A and B.
Yeah.
But what if you have like A, B, and C maximally entangled, and then D comes in and observes C? Does the entanglement between A, B, and C get completely destroyed, or is there some entanglement that's still preserved between these three things?
Okay, I think let me try to, wait, do I need to repeat because it's on? Okay. So I guess the first thing I'm going to, you said A, B, and C are maximally entangled. Okay, but we only really know what maximally entangled means between two systems. With three systems, they can have some entanglement, but they're just kind of incomparable sorts of entanglement, and there's no one most entangled one. So you might so the best I could do to say if they're maximally entangled is that if A is maximally entangled with this BC thing, that happens exactly when the whole thing is in a pure state. And that means all of the entropy of A is explained by entanglement between A and the joint BC system. maybe I can say something. This is a particularly sort of harsh way to try to take a look at what this system is. And what really one would think is happening to make the world classical is that things are bouncing off this and just extracting tiny amounts of information. But there are hundreds and thousands and millions of systems that have just tiny amounts of information about this one. And that would allow it to gradually degrade the entanglement through a process very similar to this, but instead of mapping, say, if this is in 0, mapping to 0, and if this is in 1, mapping to 1, you can imagine that you just slightly change the state. So you have some phi 0 and phi 1, and this is the state that the C system gets in when this is 0, and this is the state the C system gets in when this is 1. And these two things are very close together. So they're very hard to distinguish.
Just to clarify, entanglement metrics only exist for bipartite systems. They don't exist.
No, that's not, okay, so it is not the case. There are certainly metrics for measuring entanglement in multi-party systems, and there are measures that capture aspects of multi-party entanglement. There simply isn't a single most entangled state in for multi-party entanglement situations. If you give me a metric, I can find the one that maximizes this metric. Yeah? But then you give me another metric and there'll be some other state that maximizes that metric. And which is the real maximally entangled state? Well, the answer is there's no unique one. There's just a bunch of different maximally entangled states depending on how you measure the entanglement. I mean, even for pure states, multipartite entanglement is it's very messy.
Yeah, so I wanted to ask what quantum is good for in communication. And what I mean by this is, like, I know some things that it works for. Like, I know I can send a key down a channel and I can be pretty sure that if Eve is in there looking at this key, I can tell her presence, right? This is
Yes.
BB84 and so on. And I also know maybe that I can, send 2 classical bits with 1 quantum bit, right? Which is the idea of dense coding. But there are many other tasks that you might perform, like, and maybe, I'm just interested in if you have a list that you can provide. For example, you might want to communicate in a noisy environment and maybe quantum helps there. Or you might want to be able to communicate to somebody and prevent a jammer, an adversary coming in and stopping that communication. So there's probably a whole list actually of things that quantum are good for. And I just wanted to see if you could enlighten me.
I can. It's a funny reversal. There was a time when we got the opposite question. Which is, this can't be good for much. I would say that the list is rather short, and it's really quantum key distribution and sort of cryptography style stuff. An important one is really sort of enabling interfaces between sort of modules in a quantum computer if you're trying to build it. That's not an asymptotic scenario, but that is a scenario where you have to worry a lot about doing error correction, and you want to sort of be generating as much as entanglement as you can between, say, 2 distant systems. Of course, there's randomness generation, which people have done at NIST. To me, the reason to study this is to better understand how error correction works, and not only for the purposes of understanding how to build a quantum computer, which would be very nice, but for the purposes of understanding how error correction kind of arises in unexpected and well, in very unexpected areas of physics. So all of this stuff well, one of the things I'm most interested in, we must have talked about it, is sort of the connections between these quantum information and entanglement and sort of toy models of holography. So, I mean, I don't think anybody can, with a straight face, stand here and say there are 100 great things you can do with quantum communications. I think there are a few good things you can do with them, and I think the real reason to be doing these kinds of things is to better understand the world and to better understand quantum mechanics.
Okay, thanks, Graeme.
It's coming up on 1 o'clock, so I think it's a good time to